Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibration. In the last lecture, we discussed how the response of a simple vibratory system to periodic excitation is obtained, and as we all have seen that periodic excitation has multiple excitation functions at harmonic frequencies, and therefore, excitation is going to happen at multiple excitation frequencies. And so, the response will contain the components at different excitation frequencies. And in this particular lecture, what we are going to learn is the practical importance of a diagram called Campbell diagram, and this is particularly useful for practical vibratory systems wherein the system will have multiple natural frequencies, and also it may get excited through multiple excitation frequencies. So, finding out the resonance or critical speeds becomes a challenge and is important to know before the design is finalized. So, from the practical perspective, it is essential that we understand what a Campbell diagram is and how to make use of it. Okay. Now, we come to a more relevant implication of analyzing the response of a vibratory system to periodic excitation. Okay. Now, what we are going to discuss today is Campbell diagram, very important in the practical vibratory system analysis, particularly in industry. You do require this Campbell diagram to be plotted and used for ensuring that your system is sound from the vibration perspective. Okay. Okay, what this diagram is? For most of our mechanical systems, they are all operating with some speed of operation. You take the example of a compressor or turbine, steam turbine or anything, the rotation, the rotor is spinning with certain speed, and so what is the excitation frequency for to start with, let us say we take a simple single degree of freedom system. Okay. We take a simple single degree of freedom system having mass m and then the stiffness k. Its natural frequency would be a straight line if I represent this natural frequency on a frequency versus speed graph. Speed in the sense that suppose you have a motor sitting here rotating, its shaft is rotating and the unbalance in the motor shaft is exciting the system using this, like this. We have discussed this many times over. So, the point here is that this motor rotational speed, if I change, is this natural frequency going to change? It is not, because the natural frequency is a function of the parameters of this vibratory system k and m, and we see we see no reason why they should change. Why should k change, why should mass change? Again assuming that the system is linear and we are operating within the linear range. That means the mass is not moving with such large amplitude that you start wondering whether the k is really constant or not. With those assumptions in place, there is no reason for this natural frequency to change. So, I am plotting this natural frequency as a horizontal straight line on this speed versus frequency graph. Okay. Mind you, I have not written this as a natural frequency, I am just writing it as a frequency. There is a reason for this. Now, I have taken care of the property of the system captured through the natural frequency value. Okay. But this system has an external excitation okay, omega. Now, would this excitation frequency change with speed of motor? Whether the excitation frequency will change with the speed of rotation of the motor. Suppose I rotate the motor at 10 hertz and later on I increase the speed of rotation, the frequency is going to increase, right. What is the excitation function or excitation force to say? Now, this excitation force is m epsilon omega square e to the power j omega t. Now, obviously, the magnitude will change, the frequency will change as I change the rotational speed of it. So, when the unbalance is the excitation force or excitation source, the excitation frequency is going to change continuously with speed, and it is going to linearly change. If I change the rotation speed to 20 hertz, the excitation frequency changes to 20 hertz and so on, is not it. So, if I run it at 10 hertz speed, 10 hertz meaning 600 rpm, the excitation frequency would be 10 hertz, because that is the speed or that is the frequency with which the rotor is going to excite the vibratory system. And therefore, this graph, as the speed increases, this frequency will also proportionally increase, and therefore, you can plot this excitation frequency as a sloping line here. If both x axis units are same, you can expect this plot or this line to be at 45 degrees. What do you see from this graph now? Is this graph going to give you some more information? You get from this graph the location of resonance, right. You get from this graph the location of resonance, which is the intersection of these two lines, natural frequency line and excitation frequency line. So, the intersection between these two lines is the point where both the frequencies are same, omega which is excitation frequency, omega n which is the natural frequency. And so, what we call this point as a resonance point. Okay. So, this is for us is resonance. Now, you would ask, so what is great about it, right? What is the fun in having this kind of a plot made when we all know that I need not, I must not operate close to natural frequency to avoid resonance. This is something which we have been learning right from day one. So, what is so great about this diagram, which shows just the intersection point through a graphical means. Okay. Okay. So, the point here is, for a practical vibratory system like this, it is not only one natural frequency that we can expect it to have, right. Depending upon the kind of excitation this system get, you will have multiple vibration modes getting excited. For example, again let me come back to this example which we have been discussing many times over right from the beginning, of a windmill, a nacelle sitting on the top of the column, and then we discussed that this unbalance in the rotor blades would generate bending vibration, it would generate torsional excitation to the system, and as one extreme case can also generate the vertical longitudinal vibration, which actually means that the same operation of the rotor, the same rotor is going to excite 3 different vibratory modes. Okay. And there is no reason for us to say that the torsional vibration natural frequency would be same as the bending vibration natural frequency, would be same as the longitudinal vibration natural frequency. They will be different, of course, is not it? So, maybe the torsional natural frequency here could be maybe 20 hertz, bending natural frequency may be 55 hertz, the longitudinal natural frequency may be 270 hertz, and so on. So, I have 3 different natural frequencies to cater to. So, the excitation frequency, which is the rotational frequency of the shaft, I need to ensure that it is neither matching with this natural frequency nor with this nor with that. Okay. So, this graph which gives me the resonance point omega equal to omega n would actually now turn to multiple such resonance points. When you talk about even for single degree of freedom system, not single degree of freedom system, simple system with single mass and single spring, right, but their modes could be different. So, the same spring mass like what you see here would vibrate in 3 different degrees of freedom. So, the degrees of freedom of course will have to be 3 in this particular case to have 3 natural frequencies and therefore 3 corresponding resonances. Okay. Only thing is that your excitation function should be able to excite those modes or excite those kind of vibratory modes. So, now you can see that the Campbell diagram that we discussed here with only one crossing point, right. If I have another natural frequency, I will have one more resonance here. I have another natural frequency for this, I will have another intersection point. Okay. So, that is going to be then an important advantage of having a map or a diagram like this, which captures all the critical points or critical operating points, because this is all being plotted against the operating speed. So, the plot will give me an idea as to what is the speed at which I am expected to have closeness to one of or more of these resonances. Okay. So, we now take an example which will clearly elucidate the advantage that we were discussing about this Campbell diagram. Okay. So, I am going to take the case of a gas torque which we have seen in the initial introductory part of this periodic excitation, that this is the case or this is an example where the gas torque is not a harmonic excitation to the crankshaft and therefore to the engine, and it varies approximately the way it is shown here, and we are talking of the case of a single cylinder 4-stroke engine, okay, wherein what would happen with 4-stroke engine, that this entire cycle of repetition will be finishing in 2 revolutions. That is important, it is not going to be only 1 revolution. All of these cycles will be finishing in one rotation for a 2-stroke engine, right. So, now we are talking of 2 revolutions into a 4-stroke engine. Okay. Now, if we all know now how this periodic time function, excitation time function can be decomposed into its component harmonics. So, we are going to assume that it somehow gets decomposed into its first harmonic function, its second harmonic function, its third harmonic function. Okay. They have their own different amplitude. This is going to be A1, this is going to be A2, and this is going to be A3, and these are going to signify phi 1, phi 2 and phi 3 respectively, right. So, when you add this one to this and maybe few more of them, it will expected to recreate this particular excitation function. I have been emphasizing that the advantage of this discretization is that I can use this to get the response, I can get this individually to get another response, I can use this to individually get the third response, and then simply add them up to generate how much is the torsional vibration response of the engine when it is subjected to this kind of a torque, right. Now, there would be some additional important elements to be known in this particular example, is that the excitation torque is periodic with what frequency now? It is not with frequency rho. So, rho if it is revolutions per second, then the excitation or fundamental frequency omega naught is not going to be rho. Why? Because the entire cycle is not finishing in one revolution, it is finishing in 2 revolutions. So, we expect that the repetition frequency is going to be half of the frequency of rotation. In IC engine, it is the rotational speed that is important. In any rotating system, we always take that as a reference, like the rotational speed as the frequency. So, in our case, the torque is periodic with a frequency half of the rotational frequency. Okay. So, this repetition period is now going to be representing a frequency of rho by 2. Okay. The torque is being now in this case is periodic with frequency rho by 2. It has double the period than the period of one rotation, and therefore, the frequency will be half because they are inversely related. Okay. Now, so therefore, these coefficients that you see will be harmonic, they will be multiples of this fundamental period, fundamental frequency. Fundamental frequency is the fundamental period related frequency, which is rho by 2. So, therefore, all the components that you get, the first component will be with the frequency rho by 2, the second component will be 2 times rho by 2, the third component will be 3 times rho by 2, and so on. Okay. So, these excitation frequencies will therefore have these frequency components, half, 1 rho, 3 by 2 rho, which is 1.5, and 2 rho, and then a 5.5, and so on so forth. And they are called as engine orders. In practice, if you go to automotive industry, they will always talk in terms of engine orders. The engine order in the 4-stroke engine is going to be given by these. Okay. So, I will call the fundamental frequency of half engine order, the second harmonic as 1 times the rotational speed, and 1.5 engine order. So, this is half engine order, this is engine order, and 1.5 engine order, and so on. So, you should understand this part clearly to understand what is when someone says engine order, you should be aware of what that engine order mean. Okay. And it of course applies to this particular case. So, that engine order will have a different meaning or a value when you are talking in some different kind of an engine, maybe a 2-stroke engine, things will be different. In the 2-stroke engine, the engine order will be integer multiple like 1, 2, 3, 4, and so on. Okay. Now, coming back to this Campbell diagram, we saw that there is only one resonance here, okay, for a simple single degree of freedom system with harmonic force excitation. Now, we are talking of a periodic force excitation. Now, how this changes for a complex system like an automotive system or a complex machinery, where the machinery itself will have multiple natural frequencies and the excitation function will be periodic. So, it will have multiple excitation lines. Okay. So, instead of excitation to be this, in a typical case of a 4-stroke single cylinder engine, this is how the engine order will look like. Now, the first frequency line is called half engine order, wherein if I am operating at let us say 20 hertz, my excitation is going to be 10 hertz. For this half engine order, I mean my first excitation frequency is going to be rho by 2, our fundamental frequency omega naught is going to be rho by 2, because it takes 2 rotations to complete that repetition cycle. So, when my rotational speed, please make a note, this is your rotational speed in hertz or cycles per second. If it is rotating at let us say 1200 rpm, which is 20 hertz, it is going to effectively have an excitation frequency of 10 hertz. Whereas, the second harmonic of it, so I can go back to this particular diagram, and then what I am basically saying is that this frequency will be 10 hertz when it is rotating at 20 hertz, okay, because this is corresponding to 2 rotations. Think about it. The second harmonic component will have a frequency of now 20 hertz, exactly same as the 2 rotations. You see that in 2 rotations this is completing 2 cycles. So, for I mean this frequency has to be 20 hertz. This frequency will be, or this third component of excitation time function will have a frequency of 30 hertz. So, here you notice that the fundamental frequency is rho by 2, which is now 20 over 2, which is 10, and all the frequencies are simply multiplication to this fundamental frequency omega naught as 1 times 10, 2 times 10, 3 times 10 and so on. Okay. We discussed the case of primary and secondary unbalanced force in a crankshaft, like in the engine some time back, when I was illustrating how the response is to be calculated. Then we said primary unbalanced force is varying with the frequency of rotation, secondary unbalanced force was varying with the frequency twice the frequency of rotation. So, there if your rotation is 20 hertz, the secondary unbalanced force was having a frequency of 40 hertz. Here, because of this gas torque which varies twice in once in 2 rotations, everything is half now. So, if you are rotating at 20 hertz, the fundamental frequency is 10 hertz, the second frequency is going to be multiplied by 2 to get 20 hertz, the third one will be 30 hertz and so on. That is basically getting reflected here, that this excitation line has a slope which is not 45 degrees like what you have for the second harmonic, okay, where 20 hertz rotation speed will generate 20 hertz excitation frequency. That is your one engine order, but that is the second component of the discretized or a decomposed set of frequencies. And then 3 by 2, which is 1 and a half order, second order, 5 by 2 order and 3, and then maybe next and so on. So, if I am operating at 1200 rpm, that is 20 hertz, my excitation function will have this frequency, this frequency, this frequency, this one, this one, this one, this one and maybe more. Clear? This is very important, that if I am operating at this particular rotational speed, I have this excitation frequency, this one and that one. Now, this is regarding the excitation to the system. Now, let us talk about the system itself. Now, a system will have a natural frequency, but we are not going to have a very simple spring mass system like the one which we always show. It is going to be much more complex system. You have an engine, so many parts, engine itself mounted on some other system and so on. So, when you are thinking of that, yes, of course, it will have some a resonance which will be generated. Okay. So, this just like this particular resonance, if I am operating at a certain speed, this half engine order line is going to intersect this natural frequency and I will have this resonance, right, and so on. So, if I am approaching this particular rotational speed, okay, so this is my operating speed. When I am approaching this rotational speed, I will be bumping across these resonances as well. So, these are the two additional resonances that I need to worry about. The only thing is, these resonances will be excited by the higher frequency component of the excitation. Just like in the early example of this periodic excitation, you saw how the second harmonic was close to the natural frequency 49 hertz, and then it was very close to 50 hertz. So, the resonance was generated by the second harmonic of the excitation function. So, the secondary unbalanced force related frequency was close to the natural frequency, and that created some kind of a resonance, okay, not a primary one, but a secondary resonance. So, these resonances are actually secondary resonances or resonances generated because of the closeness of higher frequencies of the same excitation function. The primary frequency or the fundamental frequency of excitation is still this, and this resonance is the main resonance. But when I am approaching the operating speed from 0 operating speed, I will be crossing multiple resonances as I have seen here, I have shown here, okay. And then you will wonder, what about these ones? Yes, they are also the ones which will get excited. I will come back to these resonances later, but let's make things a little bit more complicated now. So, we have even for one natural frequencies these kind of resonance points identified. Now, you may have another natural frequency, right. This is fundamental natural frequency, first of the many. You may have another one, you may have another one, right, and then what do you get? Minefield of resonances, where to put your foot on, it is all scattered. I mean, you think of any position or any operating speed, chances are that you will bump into one or two or more of such resonances if you really look at the entire picture carefully. Then what do you do? So, suppose you have decided to operate your engine, at this particular speed, you already are staring at two possible resonances, all right. So, the job for you is to navigate the operating speed either here or there, right. What is the other alternative? I have not animated it here, but I may shift these lines if possible the other way, the base excitation case, either you increase the speed of the vehicle or you change the suspension for the same speed. So, either you change your operating condition or you change your system parameters, that is what you have. And I mean, this looks good on paper, but in reality both of them are difficult, okay. All right, but there is a catch here which should also be known and is usually forgotten is that what we have discussed, that when I decompose the periodic signal and I have all of these components of it, I told you that their amplitudes keep dropping, right. Right, if I have an excitation function like this, quite similar to that gas torque that I have shown you, right. If I decompose this and then plot the Fourier coefficients or all the components of the Fourier series, their amplitudes, if I plot, I told you that their amplitudes quickly decay. I mean, the higher harmonics will have less less amplitude, right. When you talk about resonance and the amplitude at resonance, what is your response? Theta. It is torque by kT. If you ignore the damping, what it is going to be? This. So, what is the angle of twist that you can expect from this resonance? Will the strength of it will not only be dependent on this amplification, but will also depend for its magnitude on the value of your excitation function, the amplitude of the excitation function. Now, the fundamental resonance, as you see here or here, this is going to be fundamental, right, because it is first line. That first line will correspond to this amplitude. But look at these ones, they are the third ones. The third one will have much lesser amplitude. So, your T3, if you are trying to evaluate theta 3, third component of the total twist, that total twist will be contributed by the first harmonic twist, the twist due to the second harmonic excitation, twist due to the third harmonic excitation. Now, the moment you talk about the third component or T3 amplitude, that is already much smaller than the first one. So, the resonance which is expected here is going to be milder in the strength as compared to the main one. So, I would rather give relatively less importance to those higher resonances here, although they will be also making an important impact. Okay. Let me tell you why. I would rather first take care of the main resonances and stay clear from them. Okay. Now, right in the beginning we discussed the whole purpose of our vibration analysis is the life of the system, did not we? If we make small mistakes in assessing the vibration amplitude, this position is going to shift higher and higher and my life is going to be shorter and shorter. Now, even if the amplitudes here are small and the corresponding stresses in the component will be of the smaller magnitude, but if it is more than this, okay, the frequency associated is also important. Ultimately, what is this? These are number of cycles. Now, if the stress reversal is happening at 20 hertz and if the stress reversals are taking place at 100 hertz, which one will be generating more number of cycles? The ones with higher frequencies. I am not bringing in the amplitude here at the moment, but the point here is that the excitation components at higher frequencies are also not to be forgotten or ignored, because they consume in a given period of time more number of stress reversal or cycles. Okay. And then finally, coming back to this point, this has the same point of discussion as we saw here. So, the point here is, suppose you have still the unbalanced excitation force m e omega square as the magnitude e to the power j omega t, and we know that if the higher frequency components which are being plotted here, these are all corresponding to higher frequencies of the decomposition. That means, we are talking of these ones which anyway have a very milder amplitude, right, plus you see that they are corresponding to low amplitude or frequency of rotation. So, these resonances are expected to be not dangerous as such. Okay. And there are other few things which will be unnecessarily complicating the point of discussion here. For example, in a rotor bearing system, the lowest modes are like rigid body modes and so on and so forth. So, the structural, the flexural modes are really not getting excited at such a low rotational speeds. Anyway, so this is what we have for Campbell diagram, and just to wrap up this particular discussion and make things even more interesting for you, is that in reality For example, we discussed the blades, right, the steam turbine blades or gas turbine blades when they are rotating, and if we plot this Campbell diagram for bringing in also the natural frequencies of the blades into picture. Now, for blades, the natural frequency line will not be horizontal. So, in case of blades, it is quite obvious and quite common to have the natural frequency to be not a horizontal line, but will be a curve tilting upwards, and there are reasons for this, which you think about it yourself. So, that is basically what the Campbell diagram is so important. It is not just getting the cross section or intersection points which you can otherwise get, but a Campbell diagram is plotted with all of these complexities, and then you can really get exact location of the resonance points, considering the fact that a system may have multiple of natural frequencies, the system will have multiple of excitation frequencies. So, there will be many number of scattered intersection points, and that is complicated further by the fact that the natural frequencies of some of the components can change with the operating speed. Okay. When the blades rotate at very high speed, they basically get stiffened at higher speeds, and that will increase the stiffness, effective stiffness, and the natural frequency. Therefore, the natural frequency will curve upwards. Okay. I hope you are clear and should now be able to understand and appreciate the practical importance of having a Campbell diagram plotted for your practical mechanical vibratory system by completely understanding your system for its natural frequencies and how they vary with the speed, and completely characterizing all the excitation functions which are expected to excite your system, and plot them to get a better perspective of where to operate your system safely away from most of the resonances. Clear? Okay, this lecture we discussed the usefulness of Campbell diagram from the practical vibration based design. The Campbell diagram allows you to have a comprehensive understanding of possible critical speeds, and then allows you to ensure that either you choose the operating speed or operating speed range looking at this diagram, or adjust your system parameters if the operating speed range cannot be changed or shifted. Then it allows you to make modifications to your design, so that your operating conditions stay away from any of the major critical speeds. So, these are a couple of questions on the basis of the discussion we had today. And you can read through the answers.